Hi again. Let's look for reduced order observer. Okay, reduced order observer, or state feedback control. We will feed the state to control them with what? With minimum order observer. So now it's not with full order observer as we saw in previous record, with minimum order observer. What is this minimum order observer? How to design a minimum order observer? Again, this is your physical system actually. So this is the physical system, the real physical system, in which you have access to some measurement. You have sensors to get some data output of it. So this is your outputs that you may need to control them later using servo design also. But now we are not talking about servo design. Servo design is we already done with it and we know. But now our problem is about the states. How to get those states. So we need to design observer to get the state in practical implementation. Once we have the state, you can do servo design as always, as we did before in type 0 and type 1 system, etc. With example of my MOO system. So now that's your physical system. You have measured the output, and your minimum order observer is this box. So it has a Y as input, it has a U as output, as input as well. So then, like the full order observer, what's the difference then? It has Y and U. Well, the output of it is not X observed state. It's not the observed state. It is actually a variable zeta, and you have another block which is, we call it the transformation block. So you have the minimum order observer and the transformation block, and this transformation block, it has an input that zeta tilde and Y as input. It has an output x tilde. So x tilde is the output of the minimum order observer and the transformation. So if you wish, the transformation plus the minimum order observer, they have inputs Y and U and output x tilde, and then later on x tilde you feed it back. Well, the K is the same as we did in full order observer, or as we are doing always, AB with the desired closed loop dynamics of the overall system, where you want to place your pole. So then K is fine. What do I have? Let's look inside now, inside the transformation block and the minimum order observer block. What do I have inside them? Well, here you can see here, this is a block diagram of state feedback with minimum order observer, in which this block is the minimum order observer and the other block is the transformation effect. Well, this is we refer to as the minimum order observer because if you look to A hat, so now not A tilde, I'm not talking about A tilde, I'm saying A hat. Okay, A hat, B hat, and F hat are actually a function of a KE. KE, which is a gain that we used to compute the minimum order observer, as we did previously in here in finding KE. And KE was the gain used to compute the full order state observer, A star, C star, and the closed loop dynamics of the state observer. So then it is basically, this is the minimum order observer because it contains KE. You cannot see KE now. If you look inside the block, you are seeing B hat, F hat, and A hat. But I'm telling you, like, it is inside this function, A hat, B hat, and F hat, you have the KE. So that's why this is the minimum order observer. The transformation, it's this block diagram, which is C hat and D hat. Well, we call them hat just to get distinguished between them and the tilde, which we used previously in here. A tilde, B tilde, remember when we used them here to actually compute the K hat for a system of type 0, right? So then don't confuse between A hat, B hat, and A tilde, B tilde. So now here is A hat, B hat. Previously we were using okay, here is the symbol of it is A hat, and now okay, my symbol is A hat, but it's in different A hat. Okay, so if maybe you can give it tilde symbol or whatever. Anyway, I think the tilde is used somewhere else. Alright, so then here is A hat. Don't get confused with the A hat which is used in servo design. Anyway, this is not servo design. Here with regulation we have R equals 0. So because we are focusing on the states. So how to compute now A hat, B hat, F hat, C hat, and D hat? We know that K is simply its place A, B, and then the desired closed loop dynamics for the system. You choose the closed loop pole location in a way you can build your closed loop dynamics. So then, what about the remaining matrices in the minimum order observer? B, A, B, and F hat, and later C and D. Those they are. Those A hat. You see, A hat depends function of KE, also B hat, and F hat. So that's why this is the minimum order observer. Here is simply a transformation, C hat and D hat. It's just a transformation. Okay. So now you may ask, so how to compute K hat? What is ABB, AAB, ABA? What IN1? You have a lot of questions, right? Okay, let's talk about them. First, what's KE? KE equal to place or acre of what? Of the following. That's how I remember it myself. Of A, B, B star, A, B star, then some closed loop dynamic for the minimum state observer. Also, you need to choose them in a way you converge quickly to your X. So your X tilde should converge quickly to your X. Or acre, ABB star, AB star, and your desired closed loop dynamics of the minimum order observer. Alright, so star again and again, it's the conjugate transpose. So it ends up to be transpose if area matrix are real. And don't forget the star here, or the transpose of everything if everything is real. The complex conjugate or the transpose. Okay, so don't forget here the star as well. Then, very cool. So now you may ask me, so what's ABB to find its conjugate, complex conjugate, transpose conjugate? What's AAB? What are those? What's ABA, AAA? Because ABA will be used here. AAA used here to find B hat. Okay, here we go. Actually, remember, minimum order observer is what? What it means? It means I don't build an observer for all my states. So I should divide my states into measurable state and unmeasurable state. right? So that's the idea behind, don't forget the idea behind minimum order observed. So assuming you have n state, some of them are measurable and some others are not measurable, and therefore you build an observer first for the unavailable states only. So then that's the idea behind the minimum order observer. The other states that are measurable, you feed them directly, okay? And therefore what you see here as x hat is actually doesn't mean that all, so inside x hat doesn't mean here in this case that all are observed. Maybe some of them are observed and maybe some others are not. So the zeta tilde is the observed state, but when you go here with the transformation, you will end up having all the states, including the observed and the measured and the observed state, both. So then, if that's the case, let me divide my dynamics into two, in which I put in one part the measurable states and in another part the unmeasurable or the unavailable states. So, and that's what we are doing here, okay? That's how we are dividing the system into, maybe we start by the measurable, and in this case I'm taking it not in bold, I'm considering simply one scalar as one output, so it's a CSO system. Later on in the exercises at the end we will see how it's extended very easily, but just to change the dimension, nothing more. So then it's a kind of CSO system here. You see your output is in bold like that. Actually it's only one line, it's not like this. So then it is actually, I'm taking one scalar as an output. So, and my output is the only measurable state, that's what I will assume. So then XA is a scalar, it's not in bold, and all the other states are unmeasurable. So I need to design a minimum order observer for n-1 state. If I have n state, so I'm assuming only state 1 is the measurable state, and the other state, all the other states are unmeasurable. So this is, for example, xb, and then this is xa, which is equal to x1. So here it's a vector in bold. So then I divide my dynamics to that. So then AA, AAB, ABA, ABB are known. BA, BB are known. They are known. Because you know A, this is at the end, this is your matrix A. But you rearrange it in a way, you start by the measurable. Don't forget, we are starting always by the measurable state, and we end up by the unmeasurable state. So in this case I have n-1 and one measurable state. Alright, my output is one of the measurable state. I'm simply taking my output as, so that's why 0 is in bold, n-1 row columns vector of zeros, and here is only one scalar, y equal xa. I'm taking my y as one of my state, which is a measurable state. Of course, y cannot be something else than the measurable state. Cannot be something else than a combination of measurable states at that. Okay, so now cool. Now you know ABB, AAB, ABA, AAA, BA, BB, BB. So all of them, you know them. And KE, you already found it by knowing ABB, AAB, so you can find KE. So then, what's remaining? Nothing, so you can have A hat, B hat, F hat, and therefore constructing this block diagram, which is your minimum order observed. What about the transformation? C hat, D hat. Okay, this is C hat and D hat. Simply, if you look to the D hat, is 1 KE. And 1 is known, and KE is known, so then this is your D hat. So D hat is known. Let's assume, just to have better understanding, enlarge it a bit for a MOO system. So assuming I have a MOO system, let's say I have two outputs, y1, y2, and let's say I have three unmeasurable state. Okay, unmeasurable states. Remember, your minimum state observer is for the unmeasurable state, for the unmeasurable, unavailable states. So therefore, if I have three unmeasurable states, so then KE should be of length 3, right? And remember, KE transpose, so that's why KE is actually like this, KE1, KE2, maybe KE3. It is like this now. It's not anymore, as we always describing it like this, a row vector. It is not a row vector anymore. It is, for the observer, it's a column vector. Why? Because it's a transpose of it. Well, in this particular case where you have two output, so then KE will be a matrix in which you have three states and two output, one output for y1 and another column for y2, and KE11, KE12, KE21, KE22, KE31, and KE32. So it's 3 by 2 matrix. That's your KE. When you have this KE for your minimum order observer. By the way, minimum order observer is abbreviated by MOO. Okay, so then let's learn this abbreviation. MOO. Okay, minimum order observer. So that's the KE for your minimum order observer. Sometimes in some textbook you find it called Lamberger mean, like minimum order observer. Okay, so it's a symbol at hand. Just know how to find it this way. So I'm saying now, what if that's my state? So I have three unmeasurable state and two output, which is maybe these two outputs reflect two measurable state. At the end I have 5 state. So then, in this case, D hat, if you want to represent D hat, okay, this one will be an identity matrix. So now I'm just extending. See how easy it is to extend it to a MOO system? Just you need to be aware about dimension, understanding your system. And dimension is a story of algebra, right? Nothing more. And then here you will be having 1, 1. So now it's an identity matrix. Instead of 1, you have an identity matrix 2 by 2. So D in this case, it is 1, 2, 3, 4, 5 line, 2 column. What about C? C, here is a vector and here is identity matrix n minus 1. So n minus 1 represent what? N1 represents the n minus 1 unmeasurable states. Remember, I was telling you who are taking only one output and n minus 1 output, one measurable state, I want to say, and n minus 1 unmeasurable. So the n minus 1 here that represents there are represented there. So then, assuming you have 3 unmeasurable states, as the case here, so assuming that system, so then in this case C hat will be 3 by 3, so 1 1 1 0 0 0. So this is your identity matrix. And what you will have here, it's also written in bold. Here you should be having 0 0 0 vector that represent your output, which is y, only if you have one output, which is y1 equal to, or y equal to xa, y equal to xa, single output. If it is MOO, in which I have 3 unmeasurable state, well, if I have n minus 1, so then you n minus 1. If I have 3 unmeasurable state and 2 outputs, as the example we take for D hat, let's do it for C hat. So then, what will be the difference? The difference here, your C is not a vector, will be a matrix of 0. Will be a matrix of 0, right? And this matrix of 0, because one corresponds to y1 and the other y2. And of course, you have the identity matrix. Good. So now you could imagine it if it is, and if you have a MOO system. That's it. That's everything about a reduced order observer. You need, at the end, you need to find A hat, B hat, F hat, C hat, and D hat. And here is the formula of finding them. You need to simply rearrange your state into measurable and unmeasurable state. You start by the measurable first, and so then you know your matrices. Also, you know your if you sub-matrices. If you know your sub-matrices, you'll be able to know here. So you construct your block diagram this way. Once you having the block diagram, that's it. You solved your problem. That's a minimum observer problem. Well, the last remark, in some books, the block diagram is not written like this. You may see it in like this. And don't get afraid from, you may see it this way. Both are the same. Just it is a rearrangement of the block diagram, nothing more. So they don't use actually, some books they don't use the A hat, B hat, F hat. So if you don't hear about just matrices, it's also alright. I will show it to you how they do it. But actually it's exactly the same. Just it's a rearrangement of the block diagram in which they still considering, of course, the minimum order observer and the minimum order observer and the transformation. They still consider them, and if you look to the analogy, try to compare them. What is C hat? So this is C hat. Well, it sounds to be 0 zeta tilde, but actually tilde is the identity matrix. So then it is C hat. No problem. So then we have here C hat, which is analog to the C hat. You have it here. And D hat is 1 over KE, so then D hat is the same. So the transformation matrix is the same here and there. So what's changed is in the minimum order observer, they rearrange it in a way they make KE clearly seeing. So they don't use A hat, B hat, F hat. Okay, this is equivalent to C hat and D hat again, so they are the same. But here they don't clearly mention in the block diagram that is called C hat, D hat, or this is called A hat, B hat. If you look at, for example, here, ABB minus KAE AAB, but this is actually A hat. Look to your A hat. It is the same. Okay, so maybe A, you can see it clearly, right? So then, this is your A hat. So then the same here, again A hat is the same here and there. F hat, it turns out like F hat also is the same. If you look to here, f hat BBB, f hat is what? BBB minus KEBA. It is BBB minus KEBA, and it is here. It is here as well. Okay, so then again A hat, F hat are the same. So just they use their expression as in the block diagram other than putting F hat. So then what is different? So then A hat is the same, F hat is the same, C hat, so then it looks like it's the same block diagram. So what's different? The only minor difference is in here, in the B hat. Look to B hat. B hat is A hat, key hat, plus ABA minus KEAAA. And it's represented here. But look at here, I actually, if you see, it is not represented this way. It is ABA minus AEAAA, that's the term of B hat. It's a term of B hat. And they actually have here A hat and they have here KE. So if you do some rearrangement of the block diagram, you get actually B hat. So you get something similar. So you up to you. You are free, and when you do in Simulink, you want to construct your minimum order. You can do in both ways. You can do it this way. This is way is right. Just I'm telling you. Maybe you see it in some other textbook represented this way or this way. Both are the same. So just it's about some rearrangement in the block diagram. So you can choose which way you want to go. Yes, that's it for the minimum order observers, the observer design, how to design the minimum order observer. It is as a resume, as a summary, you need to find A hat, B hat, F hat, C hat, and D hat simply by rearranging your system dynamics into measurable and unmeasurable state. And here I give you a good example to see how they are in MOO system. Like I'm giving the example on which I have 3 unmeasurable states and 2 outputs, how C hat and D hat will look like, how KE for the minimum order observer looks like if you have more than one input, more than one output. Okay. In addition to the unmeasurable state, because the minimum order observer, it deals with the unmeasurable states. That's it. So let's go over exercises now.